Hello, Y10. This is going to be your exam run-through for double award. And in this run-through, you're going to find out what the examiners are looking for. So you'll see the mark scheme, and you'll see what examiners can allow and what they don't allow. You'll understand how to improve for next time. And at the end of this, you'll do a self-evaluation form, and that will help you to identify the areas that you didn't do so well on, and it will help you to prepare for your Year 11 GCSEs. So throughout this video, ensure that you are making corrections. Okay, so here the diagram shows the three states of matter for a substance. You've got solid and then you've got liquids. Now you can see liquids are still together, and now these liquids are, the particles in liquid are moving. And you can see as you go from solid to liquid, you get more energy, but the particles are staying the same. So this goes on nicely to our next question, which I'll come to after this. So it's asked for you to complete the diagram by drawing 6 circles to represent the molecules in the gas state. Now you should have done this. They should not be touching because they've got a lot of energy, but as you can see, they've stayed the same size. And now it did ask you to draw 6. Now when it asks you to do something, you have to do exactly what they say. Sometimes you may lose out on marks. So six circles separated from each other. That's what the mark scheme says. Okay. It does accept a minimum of 4, but just to be safe, I would always do what the exam tells you to do. Okay, so which statement is correct about the movement or arrangement of the molecules of this substance? So if we go through each of them, we can do a process of elimination here. They move randomly in a solid state. That's false. Molecules are fixed in a solid state, so they can't move. So solids can't flow. They move randomly in a liquid state. That's true. They do move randomly. They're arranged in fixed positions in the liquid state. That's false because liquids can flow. And they're arranged in fixed positions in a gas state. That's false as well. Gases can flow as well. So it has to be B. Which term is used for a solid changing to a liquid? That is melting. Some cold water is poured into a conical flask and the bung is inserted. The diagram shows the flask after a few minutes. You've got liquid water, air and water vapor. What is occurring in the flask? Now it is condensing and evaporating. So your water here is evaporating and then it is condensing. Now it will reach a state of equilibrium because this is a closed system. Illegal drugs are sometimes used to affect the performance of racehorses. These drugs can be tested in horse urine using chromatography. So chromatography is very important. We use it in a lot of other things as well, in crime detection. A concentrated sample of urine from each horse is spotted on the start line of a sheet of chromatography paper. Known illegal drugs are also spotted on the same paper. Ethanol is used as the solvent. So it's not always water, we can use different solvents. So the chromatogram shows urine samples A, B, C, and D. So there's 4 different horses here, and the 2 illegal drugs, Lasix and Bute. So here we can see, it says, explain which urine sample contains an illegal drug. So we've got 2 illegal drugs, Lasix and Bute, and we can see that Lasix, the dots reached up here, and there is no sample which is in line with that. So none of these horses have tested positive for Lasix. But Bute, on the other hand, there is one horse here that has been tested positive, and that's because the spot is in line with Bute. So this horse will probably be disqualified. Okay, so it accepts referring to travelling distance or have the same RF value. You can say that it has the same retention factor to the paper. B, what is the meaning of the term solvent? This one's an easy one. Solvents are substances that dissolve a solute, solid, or another substance. It also forms a solution with a solute. C, the results for the known drugs are given as RF values. Calculate the RF value for Lasix using some or all of the measurements given on the diagram on the previous page. So it's quite nice that they've given you these measurements. And here, the RF value is just a decimal, or it's a fraction expressed as a decimal of how far the solvent has moved in comparison, how far the solute has moved in comparison to the solvent. Okay, so if your solute has moved half the way up the paper like this one, or half the distance as the solvent has, then this one's going to be around 0.5. Okay, so it is a fraction half, but expressed as a decimal, and you have to express it as a decimal. So these ones, so these dots here, I'll probably give them a retention factor of 0.9. They're going to be quite high because they've moved quite far up. This one here is probably going to be 0.2. Now it's asked us for this one. This is the key one that we want. Okay, so to work out this, I mean, it looks like it's going to be around 0.8 or 0.75 or something like that. But let's work it out anyway and give an exact figure. So you have to use this. This is how far the solvent has moved. It's moved from this start line to the top. Some people use this. Okay, you can't use that in your calculation because your solutes start here. So you have to use it from where the solutes start. So it's a simple calculation. You're going to have the bigger number at the bottom, that's 84, then a fraction, and then you're going to put down the distance the solute has moved, which is 63. So 63 divided by 84, and that's going to give you 0.75. Okay, it does accept any value in the range of this. Okay, so just how the solubility of the drug in the solvent affects the distance travelled by the substance. It's very easy. The more soluble the substance, the further it will travel. That's because the solvent can pick up the solute, and if the solute is soluble, then the solvent will hold it to a further distance. But if the solute isn't soluble, the solvent won't be able to pick it up and carry it very far. Okay, so this one, you have to fill out this table. So it's to complete the table. Some people, I think some of you may have missed that out, but complete the table A, B, C, D to show the relative mass and relative charge of a proton, neutron, and electron. So protons have a relative mass of 1, and neutrons, they're found in the nucleus, and that's what gives an atom all its weight. Now that the nucleus is very, 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 very small, it's in the middle, and that's where most of the mass, that's where pretty much all the mass of an atom is centered. Relative charge of a neutron is 0, it's neutral, and the clue is in the name there. Then we have proton, which is positive. Electron, you just have to remember, it is negative, and they're on the outside. And they're always the same number of electrons as there are protons because atoms are neutral. And this will help us in the next question, which is state the number of protons, neutrons, and electrons present in one atom of this isotope. So here's the isotope. Now we've got a mass number here. The mass number just tells us the number of protons and the number of neutrons in the middle, in the nucleus, in the middle part there. Okay. Now this number here, this just tells us the number of protons. So if we go to our answer, the number of protons is 1. That's how many we got. And the number of neutrons is going to be 2 because the mass number is 3. And you just minus those two numbers to get your neutrons. The number of electrons, always the same as the number of protons, is 1. What is meant by the term isotope? Now here, I would say the same number of protons, but different number of neutrons. Now, it doesn't matter about the electrons with isotopes because remember, atoms can have different numbers of electrons and they're called ions if you remember. So you don't need to mention electrons. So here in the mark scheme it says ignore any references to electrons. Okay, but just to be safe, I wouldn't mention them. Okay, so bromine has two naturally occurring isotopes with mass numbers 79 and 81. So they have the same number of protons, but they have different number of neutrons. And bromine 81 has 2 more neutrons than bromine 79. So let's use this information to calculate the relative atomic mass of bromine. Give your answer to 2 decimal places. So you have to do that to get your mark. You have to follow what the exam wants you to do, or you may not get the mark. In most cases you don't, but sometimes you will, but just I wouldn't take the risk. So in answering a question like this, calculate the relative atomic mass, we're finding an average of these two isotopes. So I would say, because they're always out of a percentage, out of 100, I would always just use the same method that we used earlier on in the year. Pretend like you have 100 atoms and half of those atoms, or 50.7 of those atoms, are bromine 79. And then the other half of those atoms, or 49.3% of those atoms, are bromine 81. So we want to find out the weight or the mass of all of these 100 atoms, and then we're going to divide it by 100 to find out the relative or average mass of just one of those atoms, because we've got 100 atoms here. Okay, so what we need to do is we need to do 79, because each atom weighs a mass of 79, and we need to times it by how many atoms we've got. We've got 50.7. Then once we've worked out that, once we've times them, we've worked out the weight, the mass of one half of this half, of the first half. Now we need to work out the weight of the second, or the mass of the second half. And each atom weighs 81. And then we've got to times that by how many atoms we have. I know it's not a whole number, so it could be, but we have 49.3. Then when we divide that by 100, we're going to get 79.99. Okay? Again, that's two decimal places. The table shows the displayed formula of some organic compounds. Explain why all of these compounds are described as hydrocarbons. Now the clue is in the name here. They contain hydrogen and carbon atoms. And if you look at them, all of these molecules fulfill that criteria. But the second mark is you have to say only. So they only contain hydrogen and carbon atoms. Okay, so you won't get the second mark if you don't say only or words to that effect, anything which indicates that it's only, so exclusively or solely. Okay, B. Why are B and E described as unsaturated? Now, if you remember the definition of saturated, you can remember the definition of unsaturated. So saturated means all bonds are taken up. So only single bonds, that's what saturated means. So unsaturated means the opposite. That means you're going to get some double bonds or triple bonds. Okay, so in this case, we have double bonds. B and E have double bonds. Which letter represents the first member of the homologous series of alkanes? Now, so we're looking at alkanes, and the first member is methane, the gas that comes out your Bunsen, comes out the gas tap for your Bunsen burner. So methane, and that's CH4. Remember, the second one is CH6, and then C3H8, and it just goes up and up and up. So methane, that is A. Which letters represent compounds that have the empirical formula CH2? Now, normally these are alkenes. Okay, so looking for any alkenes, so that's E and B. So both of these are alkenes, so they're going to have the empirical formula CH2. However, on the other hand, we do have F, which looks slightly different. We can cross off these because we know that these are alkanes, so they're not going to have this same empirical formula. But F, on the other hand, we're going to have to just check. So double check that. So here, if we write out the molecular formula, we can see if it follows this structure. We can see if we can simplify it to get CH2. So we have 4 carbons, then we have 2, 4, 6, 8. We have 8 hydrogens. So can we simplify it to make CH2? Yes, we can. So your answer is B, E, and F. Question E. Compound F has the same general formula as an alkene. So that's CH2 as we found out from before. Why does F not decolorize bromine water? So here E and F, they can decolorize bromine water because the bromine can be added along, and this double bond can be broken to form a single bond, and that happens in both of them. And then the bromine is no longer present. It's actually part of this structure, so it's actually decolorized. You don't get that brown bromine color. But on the other hand, F, you can't do that with F. There's nowhere for those bromine, these bromine atoms or molecules to bond to. So because it has no double bonds or only single bonds, so it accepts, because it's only saturated compounds can decolorize bromine, and accepts all of these other things if you just want to read through them. Okay, question F. One of the compounds in the table reacts with bromine to form G, a compound with the composition by mass Carbon, it has 22.2%, hydrogen has 3.7%, and bromine 74.1%. So it's made up of carbon, hydrogen, and bromine with those percentages, shown by calculation that the empirical formula of G is C2H4Br. So what we want to do is we want to work out the number of moles of each element in this compound here. Now it's given us the percentages of each element in this compound. Now we want to work out the moles because we want to find out if the mole ratio is equal to this. So to work out the moles, we actually need mass. And the first step when you're working out empirical formula is just write the elements first at the top, okay? Because we're going to be working out the ratio of, we're going to be working out the moles and then hence the ratio of these elements. So to work out the moles, we need mass. And it hasn't given us mass, it's just given us percentage. So we're going to have to, use our own mass here. And I suggest using 100 grams. If you use 100 grams, then this makes working out what the mass would be in 100 grams of this compound very easy, because it is going to be the same, because it's giving it us in percentages. So the mass of each of these elements is going to be this. And if you add up all those numbers, 22.2, 3.7, and 74.1, you will get 100 grams. Now you can take any number there, but using 100 grams, because we're using percentages, is easier. And then we need to work out the MR, because to work out the moles, we need to do mass over MR. So we need the MR, and to find out the MR, you just look in the periodic table and you just look at the top number there, which is the mass number. If you use the bottom number, the atomic number, you will get 0 marks. So be careful there. And the more practice you have of this, the better. So looking in the periodic table, you will get those values for mass. Now working out the moles, we're using the same equation that we've used in all our mole calculations. Okay, and that's moles equals mass over MR. Okay, so if we do that calculation with each of these, you will get the number of moles. Now make sure you do this the right way round to get the marks. Okay, so our moles for each of these are the 0.93. Okay, so these are the moles of carbon in this compound, hydrogen in this compound, and bromine in this compound. And let's see if this ratio is the same as this ratio, 2, 4, and 1. So if we divide by the smallest number, which is 0.93, each of these 0.93, then you should get 2, 4, and 1. And that is the same as C2H4Br. Okay, that's your 3 marks there. I think that's the easiest way to lay it out, but there is another way of laying it out here, which if you're interested, you can just pause the video and watch. But I would go for this method because it's easier. Okay, it's more logical, I think. Okay, question 5. Hydrogen chloride is formed in the reaction between hydrogen and chlorine. The equation for the reaction is below. Each molecule in this equation contains the same type of bonding. Name this type of bonding. So if we're looking at types of bonding, we're only looking at 3 different types, because that's the extent of what you've learned. So covalent, so we're looking at covalent or ionic, or if you're a singular order, then you're looking at metallic as well. So your covalent bond, so here we need to look at what type of atoms we've got, and we've got hydrogen, which is non-metal, and chlorine, which is also non-metal. So we're looking at covalent bonding here. Okay. The bonding in a hydrogen molecule is strong. Explain why the boiling point of hydrogen is low. Now, if you look at hydrogen molecules, you'll have hydrogen, in hydrogen gas, you'll have lots of hydrogen or H2 molecules bouncing about off each other. As in those 6 circles at the start of the lesson, they're not touching, they've got lots of energy and they're just moving around and bouncing into each other. Now, in between these molecules, there is a force in between these molecules, and they're called intermolecular forces. Now those intermolecular forces are very weak. They can't hold the hydrogen in a fixed position like in solid. So when it says explain why the boiling point of hydrogen is low, that's because the intermolecular forces between the molecules are weak, and that's what's broken in our state change. Now there are covalent bonds in between the atoms, in between the H2 atoms, but you don't need to refer to them because they are not involved in state changes in simple covalent structures. So you do not need to mention them. Okay, so you only need to mention the intermolecular forces. So your answer here is weak forces or weak intermolecular forces, therefore little energy required to overcome these forces. Okay. Now it does say here, accept bonds for forces, even though it's good practice to say forces because they're not bonds. It says reject atoms because they're not atoms, it's H2, so they're molecules. So there's weak intermolecular forces between those molecules. Accept particles. So particles is always your safe bet. If you say particles, that covers ions, molecules, atoms. So it's always a safe bet to use the word particles. And accept correctly named intermolecular forces. You won't know those, but ignore these things. Any reference to breaking covalent bonds or ionic bonds, it scores 0. So I just wouldn't mention covalent or ionic, even though there are covalent between the two hydrogen atoms. Just don't mention them. You don't need to. Okay, part C. Explain how the two atoms in a chlorine molecule are held together. Now, in this question, you can't just say covalent bonds because you're not explaining, you're just stating the type of bond. You need to explain how this type of bond holds the atoms together. Now, in your chlorine molecule, when you have two chlorine molecules held together, now they share a pair of electrons there. Okay, and when they share a pair of electrons, when they share a pair of electrons, they are held tightly together. Now, this shared pair of electrons here is, if I just draw that out again, in a bit more of a simple way, those shared pair of electrons are negatively charged because electrons are negatively charged. Then in the middle, you have the nucleus, and then the nucleus is positive. So you have the positive nucleus in the middle. So here when it says explain how the two atoms in a chlorine molecule are held together, the two nuclei are attracted to the bonding pair, the negative bonding pair. Okay, and that's what holds them together. So your first mark is the attraction between the bonding or shared pair of electrons and the nuclei of both atoms. You need to mention that there's two nuclei. You can't just say one nuclei because that doesn't hold the atoms together. It's between the two nuclei. Okay, so be careful when talking about that. You don't get the second mark if you reference only one nucleus or one atom, because that assumes that there's not another atom involved. Part D, draw a dot and cross diagram to show how the bonding in hydrogen chloride in a hydrogen chloride molecule. So it's going to be this. Now, hydrogen has 2 electrons in its outer shell, and chlorine has 8 electrons in its outer shell. You have to show the different electrons using either dots or crosses. Okay. So you get the first mark for 2 electrons shared. So you get the first mark for this, and then you get the second mark for the correct number of electrons in the outer shells of both. Okay, so that's 8 for this one and 0 for that one. Sorry, 8 for this and 2 for this, sorry. Okay, part E. Hydrogen chloride gas dissolves in water to form solution A. If we write out the chemical symbol of this, that's hydrogen chloride, that's now dissolved in water. That's actually hydrochloric acid now, as you can see from the chemical formula. Okay, so hydrogen chloride gas dissolves in methyl benzene to form solution B. You're not going to know what that forms, so that's fine. A teacher adds a piece of magnesium ribbon to each solution. So adding magnesium to the first solution, hydrochloric acid, we know that we're going to get a gas produced. We're going to get hydrogen produced. So if we do hydrochloric acid plus magnesium, we always get a salt plus hydrogen gas, and this is what causes the effervescence or the fizzing. Okay. Explain why she observes effervescence with solution A, but not with solution B. So she observes it with solution A because it's acidic. Okay, and then so hydrogen is produced, but with solution B, we can assume that that's not acidic. If it was acidic, we would get hydrogen gas produced. So that would be your 3 marks. So effervescence is due to hydrogen gas. Solution A is acidic. Solution B is not acidic. Okay. Here are some notes which you may want to read through, but I'm not going to go through them.